So section 11.7, we're going to be dealing with the ratios of areas of different shapes. So the first method that you could potentially use to solve these problems is to simply find the area of each shape that you're looking for and then write it as a ratio, which is what you would logically think to do, right, if you were presented this problem. So for example, if I had this rectangle and this triangle, and I said find the ratio of the area of the rectangle to the area of the triangle, you're naturally going to figure out the area of the rectangle and then the area of the triangle, and then write it as a ratio and making sure that you have it in the correct order. And since the rectangle came first, it's going to go on the top. So you get 50 over 30, which you would reduce down to 5 to 3. So that's the natural way of thinking about it, which you could potentially do for every single problem, except there's going to be some problems where they don't actually give you enough information to figure out the area of each shape. So what do you do then? Well, this type of situation is usually when they give you two similar figures. So maybe two similar triangles or two similar pentagons or something, and they only give you, say, a pair of corresponding sides or segments that you would know the length of. Instead of actually calculating the area of each shape and then writing it as a ratio, the shortcut would be to take the pair of corresponding segments that you have, S1 and S2, write that as a ratio, but square them. And you think about area, the units are squared, right? So it's a square unit that you're thinking of. Well, the sides themselves would need to be squared to write the ratio of the areas. And it doesn't just have to be sides. It could be any corresponding segments that you have. Okay? So here's an example where we have these two triangles, 1 and 2, and they're similar to each other. The only thing we know is the bases. One is 6 and the other is 4. So we don't have enough information to actually calculate each of the areas, but using this formula up here, we can say that we take this side and square it, and then put it over that side and square it. So 6 squared over 4 squared, which you could typically just, 36 over 16 and then reduce it. Or a nice method is that you can take this fraction, 6 over 4, and since both of these are being squared, you can treat it as a fraction, the whole fraction that's being squared. So what that allows you to do is actually simplify this fraction before you square something. And that could be really useful if, say, you don't have a calculator with you, and what if these numbers were really large? You can simplify it first and then square it instead of taking large numbers, squaring them, making them even larger, and then trying to reduce. Okay, so this reduces down to 3/2 squared, which gives me 9 over 4. And you can totally see that with this being 36 and this being 16. Both of those you would divide by 4 and you get the 9 to 4 ratio anyway. Okay, that's it for the ratio of areas. You just have to pay attention if, are the shapes similar or not. Now the next thing is what do they mean by corresponding segments? So say you have two triangles that are similar, then you could use a pair of corresponding altitudes, medians, or angle bisectors. It doesn't have to be a pair of sides, right? You could also think of, say, two circles. Corresponding segments in circles would be radii or diameter, right? So lots of different options there. All right, so then our last theorem that we're going to talk about today is talking about the median of a triangle and how it divides the triangle into two triangles that have equal areas. Now, we've already established that these two triangles are not going to be congruent. You can tell right away. This triangle's obtuse, this one's acute, not going to be congruent. But this is the median, right? So we know that these two segments are congruent. That would be considered the base of each triangle. And then if you were to drop down the height from point B all the way down here, you can see this is H, okay, and this is B, and this is B. Ooh, good writing, Miss Romander. Okay, so the area of this triangle right here, 1/2 base times height, and then the area of this obtuse triangle is 1/2 your base, but this is also the height because it's the obtuse triangle, it falls outside of the triangle. So the area of both of these is going to be congruent or equal. All right, so that could be a useful theorem to keep handy. All right, that's it. Talk to you later.